Section 8.5, Using Intercept Form. What we're going to look at today is a different format for the equation of a parabola, or a quadratic equation. In the past, we've looked at standard form, which is f of x equals ax squared plus bx plus c. We've looked at vertex form, which is f of x equals a times x minus h squared plus k. And today we're going to be looking at intercept form, which is f of x equals a times x minus p times x minus q. What this does is it quickly gives us the two x-intercepts of a parabola. Those intercepts are p and q, the numbers that are being subtracted from x in our equation. So it's similar to in vertex form when we had x minus h. The h was our x-coordinate of our vertex. Basically, whatever number you see, you want to use the opposite of it. If it's positive, you'll use the negative. If it's negative, you'll use the positive. What's nice about the x-intercepts is it shows us 2 points on the graph. 2 points where the parabola crosses the x-axis. And the axis of symmetry is nicely in between these 2 points. So I'm going to take the two numbers, p and q, add them up, and divide by 2 to find their average. That will give me the equation for the axis of symmetry that's in between them. On this particular example, I have y equals 1/2 times x minus 5 times x plus 3. Immediately, I can know my two x-intercepts. Just by looking at the equation, I see that the first part is x minus 5. That's my first binomial factor. What value of x will make that 0 is 5. 5 is being subtracted from x. So I have 5 is my first x-intercept, and the other one is whatever's being subtracted from x in the second binomial factor. Well, it's x plus 3, so I want to think that's x minus the opposite of positive 3, which is negative 3. And you can see from the graph, here is the x-intercept of 5, here is the x-intercept of negative 3. Now to find the axis of symmetry, all I would have to do is add those numbers up and then divide by 2. So I'm going to take 5 plus negative 3, and that equals, now plus the negative is a minus, so that's 5 minus 3, which is 2. And then I just do 2 divided by 2, which is 1. That tells me x equals 1 is my axis of symmetry. And you can see that's the vertical line that I have right here. X equals 1 goes right through the vertex. Once I figure out the axis of symmetry as x equals 1, I then plug 1 in to my equation to figure out the y value at the vertex. So I'm going to have y equals 1/2 times 1 minus 5 times 1 plus 3. And as I go through this, I'm just going to make sure I keep track of negatives and positives. So 1 minus 5 is negative 4. 1 plus 3 is 4. And so I'll multiply those together. 4 times negative 4 is negative 16. And half of that is negative 8. And you can see, therefore, that the vertex would have the coordinates 1, negative 8. That's exactly where this vertex is. X out to 1, y down to negative 8. And in order to generate the graph, we'd already have those two x-intercepts, and we'd have our vertex, and that would be sufficient. We could just draw a smooth curve through there, and we'd see that this opens up because 1/2 is positive. It's slightly wider than normal, and that's all we would need. All right, so now let's use what we've learned to graph f of x equals negative x plus 1 times x minus 5. First step is to determine the x-intercepts. Right away, I just look at my equation, and I look at the two binomial factors. I ask what's being subtracted from x. For x plus 1, what's being subtracted is a negative 1. It's the opposite of the one that we see. And what's being subtracted from x and x minus 5? That would be 5. So my two x-intercepts are negative 1 and 5. Now I'm going to average these two values to determine the axis of symmetry. So that's going to be negative 1 plus 5, and I'm going to divide that by 2. Well, negative 1 plus 5 is 4, and 4 divided by 2 is 2. So my axis of symmetry is x equals 2. Now I just need to find the vertex. I'm going to use the axis of symmetry, realize that goes through the vertex, and I'm basically looking to figure out what is f of 2, which is negative x plus 1. But instead of x, I want to plug in 2 there. And then times 2 minus 5. Now that's negative 3 times negative 3, which is going to come out to be 9. Should be exactly 9 right there. So I have my vertex at the point 2, 9. And that's all that I really need. I'm ready now to plot these points and connect them with a smooth curve. So the points I'm looking for are the x-intercepts at negative 1 and 5, and then a vertex at 2, 9. So I'll start by putting my x-intercepts in at negative 1 and 5, which are along the x-axis. And then my vertex is at 2, 9. And now I just connect them with as smooth of a curve as I can create, trying to make it somewhat symmetric. Oh, it's a little ugly. Let me try that one just a little bit more here, see if I can fix that up. I don't like the way that looks. We can do better than that. It looks at least slightly better. And that's our parabola. That's a good enough graph. That's even better than a sketch. We can see that it opens down because my lead coefficient was negative. It doesn't open any wider or more narrow than a standard y equals x squared, but that's all we would need. All right, hope this makes sense. Let's take a look at a problem that's just a little bit more complicated. Starting off with f of x equals 2x squared minus 8. So this is not in intercept form, but what I'm going to be able to do is put it into intercept form by factoring. So one thing I can do here is I can factor this by taking f of x equals 2x squared minus 8. And first, as always, looking for our greatest common factor, which in this case is 2, leaving behind x squared minus 4. And then what I need to recognize is that x squared minus 4 is a difference of squares. And so that's x plus 2, x minus 2. I also can't ditch the 2. The 2 has to stay with me the whole time. This right here is enough information to determine my x-intercepts. The x-intercepts will be the two values that make this function 0. So I'm looking at what's being subtracted from x in these two spots. That's going to give me negative 2 for the first one, and then 2 for the other one. So those are my x-intercepts, are negative 2 and 2. In order to figure out the axis of symmetry, I'm going to add those numbers together, divide by 2, and kind of conveniently, that's just 0 over 2, which is 0. And then, in order to figure out the full vertex, I'm just going to plug in f of 0. Now, at this point, you're welcome to either use the intercept form method or the original method, whichever one works best. I'll use the top method because what happens when I plug in a 0 is the 2x squared will disappear, leaving just the y-intercept and the y-coordinate of the vertex of negative 8. So, because my vertex is 0, negative 8, and my x-intercepts are negative 2 and 2, it's pretty easy to plot. 0, negative 8 is down here all the way at the bottom of the coordinate grid. Then I've got positive 2 and negative 2 as my x-intercepts of this function. And I'm just going to connect them with a smooth curve. Try to be as symmetric as possible. And I feel pretty good about that one. You'll notice opens up. The 2 was positive. It shifted down 8 units. That's where its vertex is. It's narrow because the coefficient is 2, which has an absolute value greater than 1. And that's all that it takes. You just factor it, figure out the x-intercepts, and then the axis of symmetry is always directly in between them. So that's where the vertex is located. In this case, it's x equals 0 was our axis of symmetry, which I guess I didn't actually write. We'll reference that down here. But that's the entire idea. That's all you would need to do. So one thing we've looked at in the past graphically are the zeros of a quadratic function, and we know that those are the same thing as the x-intercepts. And since what we're talking about in this section is the intercept form, it makes sense to bring back the zeros. We have kind of a fancy definition here that says that if x minus n, this binomial, is a factor of a polynomial, then n is a zero of the function defined by the polynomial. So basically what that means is if I can take f of x and rewrite it in this format, the intercept form, a times x minus p times x minus q, then if I plug in p or q into the function, I should end up with 0. And I can check that just by plugging in and going through it, but it's a nice convenient way to get there. If I need to determine the zeros of these functions, I don't necessarily want to graph in order to look at it. And so what I would do is I could just put it into a factored form and then solve that equation, solve each mini equation for 0 and see what my zeros are. To start off with f of x equals negative 2x squared minus 10x minus 12, I'm going to start by factoring out a common factor. And if it's possible, I try to take out the negative so that I can leave it as an x squared. Now when I do that, negative 10x divided by negative 2 is plus 5x, and negative 12 divided by negative 2 would be plus 6. Now if it so happened that it was plus 12, I'd leave a negative 6 at the end. If it's a positive, you're taking out a negative, you can just make your answer negative. Now that should factor kind of nicely. I'm trying to answer the question, what multiplies to 6 and adds up to 5. So I see that that's going to be x plus 3, x plus 2. And of course you could switch the order of these two here. It could be x plus 2, x plus 3. But from that, then I can quickly find my two zeros. X plus 3, if that's, what's going to give me a 0 from there? Well, what's being subtracted from x is negative 3. So my zeros for this function are negative 3. And then what's being subtracted from x for x plus 2, that would be a negative 2. And so those are my two zeros. If I wanted to graph them, I could put those as x-intercepts. If I wanted to find the vertex, I'd find the average of these two things, which happens to be in between negative 2 and negative 3 would be negative 2 and 1/2. So I'd have some decimals that I'd be dealing with, but that happens, so nothing to worry about there. And that's what we'd be looking at. All right, so looking at the second one, h of x equals x minus 1 times x squared minus 16. I actually noticed that it's already almost in intercept form, and I just think that I could actually factor it a little bit further. The x minus 1 is going to stay, but x squared minus 16 is a difference of squares. So I could write that as x plus 4, x minus 4. And from that, I'm actually going to end up getting 3 zeros. And if I have 3 zeros, a little accent there, I guess, I can get a 0 from each one of these. So from x minus 1, the 0 would be 1. From x plus 4, it would be negative 4. And from x minus 4, it would be a positive 4. And so those are my 3 zeros here. And the fact that I have 3 zeros actually tells me something interesting. It tells me that this function is not a quadratic. It actually tells me that it's a cubic function, something that would have a degree of 3 if I were to multiply it out. But the same properties from the quadratic function would still hold. Now the one problem that we might see is we might end up with no zeros. We might be unable to factor it and end up with no zeros of a function. It seems like a problem. It's actually not a problem. It's something that we would expect to happen, and we'll deal with that in the coming sections going forward. All right, I just want to look at 3 quick examples where intercept form is not actually going to help us out as much as we'd like. This first example, f of x equals x squared plus 4x plus 4, if I try to put it into intercept form, what I would get is that I get x plus 2 times x plus 2. Or perhaps we write that as x plus 2 squared. Now, the difficulty here is that I actually am only going to have one x-intercept. My x-intercept here is just going to be negative 2, which is also the same location as my vertex. And so there's nothing that I can do here in order to graph both the vertex and the intercepts and connect a smooth curve through those points. So I could figure out the vertex and then pick other points in order to solve, but x-intercept doesn't help us any more than just the vertex would here. In the second example, x squared minus 3, it's not factorable. It's what we'd call prime, so I can't put it into intercept form. It doesn't mean that I couldn't find the intercepts another way. I could, actually, just by setting x squared minus 3 equal to 0, adding 3 to each side, and realizing that x would therefore be either the positive square root of 3 or the negative square root of 3. We'll look more at that in the future. But I could get answers for that. I could find the intercepts. It wouldn't be through intercept form. So intercept form wouldn't be helpful there. And then finally, the final example, x squared plus 4, it's also not factorable. It's prime, just like h of x was. But in fact, this has no x-intercepts. And that's something we'll look at in the future as well. But basically, even if I tried one of these other methods of solving for the x-intercepts, I'd end up getting that x squared would equal negative 4. And there's not a single number that I can square and get a negative answer. So I can't put it into intercept form. And even if I could, there are no x-intercepts for this equation. So that's where it would run out. But most of the problems that we're going to look at, intercept form will be useful and applicable. And so I hope you find it helpful going forward.